Okay, we're going to continue with our second part of the 6.6 lesson. So yesterday we looked at the partial fractions, which was used when we had a quotient rule set up. So remember that was questions where we had something like an integral of a polynomial like 3x squared minus 6x plus 2, and we're dividing it by like x plus 1. So we used long division to change the question into a bunch of factors, and then our remainder ended up being a natural logarithm. Today's stuff, what we're going to do is we're going to shift gears and look at questions that would involve a typical product rule. So the method we're going to use today for product rule is called integration by parts, but before we get to it, let's do a little bit of review. So far we've done questions where we've had things that look like a product rule, but we could easily change them into a power rule. So for example, if I gave you something like this, it would be a lot simpler just to FOIL it out and do it as a regular power rule. So if we FOIL this one out, we would get minus 9x plus 18, and now just doing reverse power rule would work just fine. Or even if I gave you something that was similar, but squared. So we could FOIL that one out as well, or we could do our reverse chain rule. So if we did our chain rule, we'd raise our power, divide by 3, and in this case we'd have to divide by 1, so it wouldn't really do anything. So that would be our answer for that one. It's no longer an integral, that would be our solution. So we can kind of see we've sort of done a power rule or chain rule setup. But what happens now if we get a question where we have a product? So let's suppose we have x times x squared minus 4 cubed. That was still okay as a chain rule, because when we did our reverse chain rule, we raise our power and divide by 4, that didn't work necessarily, but we also divide by our derivative of the inside, so we divide by 2x as well, so that x would cancel, and then we just get a coefficient of 1/8, and the rest of the question would be okay. So whether it's a complicated chain rule or a basic one, the chain rule is still a good option. What we're going to look at today is what happens if we can't get that x out front to cancel. So if I gave you something like that, the chain rule isn't going to work, because if we try to follow the same strategy, if we raise our power and divide by that 3 and divide by 1, that would be our solution. But if we do the derivative of this, it will not turn back into that, because that extra x is causing a product rule situation. So we'd have to do our f times g prime plus f prime times g to get it to work properly. So those are the scenarios that we're going to look at today, is what happens when it looks like a product, but there is no other way of doing it. And they could be polynomials like that one, or we're going to look at things like x times cos x. And that's another one that you could see there's no way that a derivative of cosine would get us to cancel out that x value. So that's what we want to look for. Can you do the derivative of one to cancel the other? If you can, the chain rule type method would work better. If you can't, then we're going to have to use integration by parts. Okay, so here's where we left off yesterday. So the integration by parts is basically we just take the product rule and work backwards. So if you remember in math, we can do all kinds of things to solve an equation. So if I gave you something like x plus 4, we could just subtract the 4 on both sides to solve it. If I gave you something that was like 3x equals 12, we could divide both sides by 3. Then as we progress, we got into things like squareds, so we would square root both sides to solve. We even got into trig, so if I gave you something like sine equals a half, we would undo the sine by doing a sine inverse on both sides. So then the sine and the sine inverse would cancel, and we just get inverse of sine of a half, and that would give us 30 degrees or whatever. In Math 30, we even got into scenarios where if we had exponential equations that we couldn't make the same base, we would do the log of both sides, and that would help us solve it as well. So this whole idea of doing the same thing on both sides of an equation is actually a really good way of rearranging formulas as well. So if we take our original product rule formula, so you can see I've got it at the top here, but let me kind of rewrite it. It might make a little bit more sense. So if we take our original product rule, which means if we do the derivative of f times g, that gave us f times g prime plus g times f prime. And the order doesn't matter, we can put it in whatever we want. But the idea now is to solve this, we're going to actually do the integral of both sides. So the integral on the left side, the integral and the derivative cancel out. So we just get f times g. And then on the other side, we have the integral of two things being added. But we've been doing it all along. If I give you the integral of x plus 3, we just do them each separately. So we actually change that into the integral of x, which would be 1/2 x squared. Integral of 3 would be 3x. We just do them separately. So we can actually rewrite it as two separate integrals. And then what we want to do is actually solve for one of them. So it really doesn't matter which one we solve for. Let's just move the second one, this one here, to the other side. So our formula, you can see at the bottom here, is exactly that. It's f times g minus the fg prime integral gives us the integral of fg. So it's just written in the other order. So that's the formula we're going to use to apply this backwards product rule. So it works very similar to product rule. We got to identify which one's the f, which one's the g, and then we do just like we do with the product rule, except we're going to be doing some integrals, not just derivatives. So let's try it for this first example. So our formula, let me rewrite the formula so we can kind of follow it. So it's the integral of fg prime equals f times g oops, I don't know what's going on here. Okay, I seem to get it working now. So it's fg prime would equal f times g minus the integral of f prime g. So that's the formula we're going to work with. So just like we did normal product rule, we got to take the question and try to break it into our f and g. The difference is this is what we're starting with now. So we actually have to identify one as f and the other one as g prime. And which one you pick as each will matter. Sometimes the questions will work both ways. Sometimes it'll only work if one's f. Other times it has to be the other one as being f. So you got to play with this a little bit. So if we call our f the x term, we do the derivative of that one, which would give us 1. But for the second part, we're starting with g prime as our cosine. So we would do the antiderivative to solve for g. So in this case, the antiderivative of cos is sine. So that doesn't seem much different than the product rule, but now when we plug all of these into this formula, it should work out. So you can see we will get f times g prime, so that's those two diagonals is our question, the integral of x times cos, which is what we want. And the answer is going to be the derivative of the top two, or not the derivative, the multiplication of the top two, which is x times sine x. And then we have to do the integral of the other two diagonals, which would be 1 times sine. So you can see what we're doing with this question is we're taking an original integral that has x cos x, and we can't do that because there's two x terms, but by doing this integration by parts, we eliminate the 1x. You can see the 1x turn to just a 1. And that should work. So now our first part we're done. X sine x is finished. We don't need to do anything with it. The integral of sine we can do, gives us negative cosine. So if we simplify that, we would have x sine x plus cosine, and we would put a plus c on once again. And that's it. So that's our final derivative, our integral answer of that original question. If you wanted to see if you did it right, we could go back and do our product rule again. So let's just quickly look at it. So if I did f as x and g as sine, you can see it does what we have above. So when we do our normal product rule, we would have, here actually I'll just erase that. Let's just do the product rule from the original part. So you can see when you do your crisscross, you'd have x cos x plus 1 times sine x. Then when we do the derivative of the cosine, that would give us negative sine. And you can see that those positive signs and negative signs cancel. So we do get the one term that we wanted. So just like product rule, when we did product rule, we ended up getting like two separate terms, one being added or subtracted with each other. It works the same with integrals. So you should typically get two. Okay, so here's another one. Looks fairly similar, except it's a ln. So if we try the same thing, if we call fx and the g prime the ln x, let's see what happens. If we do the derivative of x, we get 1 again, so that works good. But now if we do the integral of ln x, we're in trouble. The derivative of ln x is 1 over x, but the integral is something like x ln x plus x or minus x, I think it is, something like that. And you can see now if we do our formula, it's actually going to make it worse. We turned our integral into something that had x ln x, and now we're going to have x ln x minus x. So we've actually made the question worse than what we started with. So if that's the case, all that means is we've labeled our f and g backwards. So for this one, the better way to go is kind of the reverse of what we would normally think, but it should work better. So if we call the ln x our f term, that derivative we can do, it's 1 over x. If we call the x our g term, our g prime, sorry, and we do the antiderivative of that, that gives us 1/2 x squared. So it almost looks like it's not going to work, but when we plug it in our formula, we would now get f times g, so that's 1/2 x squared times ln x. So that's okay. And then we would subtract the integral, but now when we multiply the two diagonals, the 1 over x will cancel with the 1/2 x squared, and we'd end up just getting 1/2 x dx. That integral we can do, that's just a simple power rule one. So our final answer would be x squared divided by 2 would turn it into a quarter. So we'd have 1/2 x squared ln x for the front part, and then minus 1/4 x squared for the second part. So when you're doing these questions, if it doesn't work by labeling the f and the g the one order, you don't get an integral that's going to work very well, you're better off just flip your f and g around and then try it again, and usually that's all you need to do. Okay, here's another example. We have integral of x times sine 2x. So this time let's try our regular way. Let's call f the x term, g prime the sine 2x, and let's see what happens. So f equals x, that derivative would be 1. If g prime is sine 2x, its antiderivative would be negative 1/2 cos 2x, which is okay. So now when we do our formula, we would have f times g, so that'd be negative 1/2 x cos 2x, minus the integral of our diagonal ones, which would be just 1 times negative 1/2 cos 2x. And we got rid of the x, so that should work. So the antiderivative of negative cos would be negative sine, and we'd have to divide by 2 again, which would give us a quarter. And that's it, and you can see we can basically change them to plus. The minus minus would become a plus. Make sure we put on our plus c at the end, and that should be it. So it's quite common when you're doing these that we get coefficients that end up being one's double the other. So we have a quarter, double that, you'd get a half. That's a very common thing, and the rest of the equation should look quite similar. Okay, I got one more here for you, very similar again. So again, this one should be okay if we have that one as the f and that one as the g prime. What some people do when they try to decide which one to do it is you want to make sure the antiderivative works out to be similar or pretty easy. So when we did the antiderivative of the sine, we got cosine. When we did antiderivative of ln, it didn't work. So that's why we kind of switched that other one around. This one, the antiderivative of e to the 2x, is still pretty good. We get e to the 2x when then we divide by 2. So that's good. The forward derivative, typically we want to try to make it easier as well. So in this case, x divided by 2, that forward derivative would just be 1/2. So if this one gets easier, that's a good sign, and you want to make sure your antiderivative doesn't get any harder. If it stays the same or gets a bit easier, that's a good sign as well. So this one should work. If we plug it in our formula, we would have f times g. So we'd have 1/2 times 1/2, which would be 1/4 x e to the 2x. And then we'd subtract our integral of 1/2 times 1/2, which is 1/4 e to the 2x. That integral we can do. It's pretty straightforward. So we would keep it the same and divide by 2 again, which would now be 1/8. And we can stop there, or because they're fairly similar terms, we could even common factor out a 1/8 out of each. So 1/8, and we can take out an e to the 2x even. So we'd get left over with 2x and just minus 1 for the second term. You don't need to do that, but it's definitely worthwhile in some of these cases where both parts of the equations are fairly similar. And that's it. That's it for integration by parts. That's it for this unit, and that's it for this course. We've now finished all of Math 31. So we'll do a bit of review, and we'll do our last test, and that'll be it for this course, and no more videos. Take care.